Welcome to the Philadelphia chapter of Informs. I'm excited to have Professor Robert Vanderbei with us. Bob is one of these amazing folks. He's a professor of OR and financial and engineering, but he's also has courtesy appointments in the Department of Math, Astrophysics, Computer Science, and Mechanical and Aerospace Engineering. I've got to mention Bob is a professor at Princeton. He's also a fellow of Informs and of various other mathematical societies. He was the chapter president of the optimization and computer science sections of Informs. I'm kind of afraid that if I go through the entire list of Bob's achievements, that I won't have time for Bob. He's going to be talking about a brand new way that Bob and a couple of his co-authors found to project spherical surfaces onto flat planes, which is useful for map making. Before I begin, I'd like to also introduce the Philadelphia chapter of Inform's Vice President, Ariel Rodriguez. And Ariel, could you say a few words, please?
Yes, hello everyone, and welcome to our first session of the year in 2022. We have plenty planned for 2022, and we have some new members also in the officer roster. And I thank you for taking out the time to to attend the sessions and just stay in touch. We'll be reaching out to communicate some of the things we have planned for the year. And thank you, Bob, for joining in this first session, and we're looking forward to hearing your talk.
Thank you, Ariel. All right, shall I get started? Can everybody hear me, I hope?
Yes, we can.
Sounds good.
Okay. All right, let me share screen. Share screen. Let me pop up my lectures, my slides, and let me go into full screen. All right. Okay. So yeah, thank you for inviting me to do this talk this evening. I think it's going to be a lot of fun. I hope you all enjoy it. Yeah, so I'm going to talk about a new flat map, which I make by doing a stress minimization problem. So the word minimization makes it sound like an operations research topic, and that's why I think it's appropriate here. But before we get into the technical details, let me mention that part of the reason I and lots of other people have been excited about this is that our map made it into the Times magazine's Best Inventions of 2021. This is the cover of the November issue, and this is our map right here. And the subtitle here is A More Accurate World Map. I hope everybody can see my cursor because I'm going to be using my cursor a lot to point at things. So please, if you don't see my cursor, please tell me right now. Anyway, yeah, so this just a few months ago was in Time magazine. This is something I've been working on with my co-authors about a year ago. And so I thought I'd show you inside Time magazine. Here's the little brief description of our contribution, A More Accurate World Map by my colleagues Richard Gott and Mr. Goldberg. So that's how they show it, and they have a little description of the map. But rather than reading that, I thought maybe I'll just stop the screen share briefly and show you it. Here it is. It's a two-sided thing. So here's here's it is on one side, and flip it over, and here's the other side. And if I put my fingers like right here in Africa and flip this over, I'm still in Africa. So there's a continuity between the front and the back as well. And so that was part of the reason that it's very cool. Okay, let me reshare the screen. Is oh, what did I do? Back to meeting. Where's the screen? Oh, where's the screen? It's because I went in full screen mode and I'm not seeing it. How do I get to preview, view? Not this. Escape out of that. Where is it? Oh my goodness. Hold on a second. I don't know what I did wrong. I'm screen sharing. How do I get to the other screens? Let me window show. There we go. Flat maps. There we are. Sorry, not very good at these things. Sharing full screen is a mess. Okay. So before I talk about the details of our map, let me do a little bit of an introduction by showing some of the classic map projections that have been out there for hundreds of years in most cases. So here's a very simple one called the equirectangular map. And the coordinates here are shown the latitudes going up 15 degrees each row, and the longitude is changing by 15 degrees with each mark here as we go across the equator here. And so at the equator, this fact that this is a square is proof that 15 degrees this way and 15 degrees this way are the same distance-wise. And so the distortions at the equator are zero. There's no distortions at the equator. But as we move up, if you go all the way around, the circumference is much smaller up near the North Pole and down near the South Pole. And so it's been stretched out horizontally dramatically. And as you reach the North Pole, it's been stretched infinitely big because the North Pole is supposed to be just one point, and it's been stretched to about 24,000 miles, the same as the equator. And so Antarctica, for example, which is a pretty big place, but it's not nearly as big as what we're seeing here, because things near the poles get stretched a lot. But yet this projection does look nice, because, you know, look at the United States of America, look at Africa, look at Europe. They all look fairly reasonable. Of course, Greenland is not nearly this big as what we see here. And so as we get closer to the poles, the distortions get large. In fact, also Alaska is a big state, but it's not nearly as big as what we see here. So there are obvious distortions in this map. So this has inspired people to make lots of other variations. Here's the Mercator projection. And here what has been done is now the vertical dimension has been distorted to equal the distortion that we were seeing in the horizontal, so that we're not seeing, you know, if I go back here, Greenland was stretched wide, but vertically it was still okay. And so that's why it looks weird. But now we go over here, now it doesn't look weird because I've stretched vertically to match the stretching that we did horizontally. And so now it looks nice by itself, but of course Greenland's not this big relative to the United States, for example. And so we've made the vertical and horizontal look nice, but the whole size of things as we get close to the pole is huge. In fact, look at Antarctica here. Antarctica looks huge, huge, huge. And so that's a disadvantage for this projection here. Here's something called the Winkle triple, which tries to mediate these two issues that I was just showing you on the previous two maps. But the disadvantage here is that there's some twisting of things. You know, United States looks like it's tilted a little bit as it angles up toward the North Pole, and the North Pole's still infinitely bigger than it's supposed to be, because it's supposed to be just a single point, and it's still here, you know, several thousand miles across. So there's still lots of distortions here. If we go on to the next one, this is called the Nicolosi map. I actually don't know the details of this one. My colleague Richard Gott does, but this is a pretty nice one. But one of the complaints that cartographers would have about this is that we've cut it here. You know, this point over here is very close to this point over here, but yet it's because it's been cut and shown as two circles, or two discs next to each other. The fact that we've cut it is considered to be a bad thing, even though the two halves look good individually. And here's the ATOF projection, which keeps the North Pole as a point, which is good. But now, you know, United States looks even more tilted and a little bit distorted because of that, as does Australia. So there's all kinds of issues as we try to do this. Here's the Mulwide projection, which is a very popular one, maybe one of the best. Here's the Lambert map, where now we've compressed vertically to counterweight the stretching that we did horizontally. So now Greenland looks terrible, north-south versus east-west. But the area of it now is accurate, and the area of Antarctica is accurate, even though the distortion between vertical and horizontal stretching is terrible. And so Canada and Alaska also, and Russia, I mean, everything pretty high up or pretty low down look very, very distorted, even though the area is correct. And here's another map called the Wagner map. Maybe I don't really know much to say about that one. And here's one that's going to play an interesting role in everything I'm going to say for the rest of the hour here. This is the azimuthal equidistant map. And so we're focused on the North Pole here. And of course, longitude is just, if we're doing this in polar coordinates, longitude is just the angle in polar coordinates here. And then as we go out this polar coordinate map, the radius here is the latitude going linearly. So here we are at 90 degrees, we go halfway out and we're at 0 degrees, we go all the way out and we're at minus 90 degrees. So the rate at which the latitude is changing is linear over the radius. And so that's why it's called equidistant. And this is both good and terrible, because Antarctica is terrible. It's huge. And as we go out further, Australia looks way too big as well. Look at Australia, looks much bigger than North America. But if we just focus our attention on the Northern Hemisphere, this little red line here, or purple, whatever color it looks like on your screen, this is the equator. Things above the equator, if you just sort of restrict your attention to things above the equator, it's not perfect, but that looks pretty good. And so the maps that I'm going to show you are going to focus on exactly that property, that this half, the above the equator half of the azimuthal equidistant projection is good. Okay, so there's lots of distortion metrics: skewness, flexion, isotropy, area, distances, boundary cuts. And my colleagues Goldberg and Gott spent much of their lives doing research into this and finding which projections optimize. But of course, as we're optimization people, operations researchers, we know that if there's 6 different objectives in an objective function, what's optimal depends on how do you combine these six different objectives. And that's not 100% clear, but people in cartography have spent a lot of time thinking about and discussing, and that's not the topic of today's conversation. So I won't go into those details, other than to say that historically, in the recent past, the Winkel triple was considered the best weighting of these different metrics. But let's focus on the new thing that I'm associated with, And that is this projection here, the Gott, Goldberg, Vanderbei map. And as I already showed you, this is not two disks side by side. That's just the way I'm going to show it to you on the screen here. But the reality is really just one thing. It's like an old record that you play on a record player, for those of you who are old enough to remember these things. And we might call this the side A and side B of a record. And so the side B is on the back of side A. But I think what's clear here is if I turn this over, flip the one on the right to the back of the one on the left, that Africa here will just be continuous. And so as I already showed you a little bit, I can go from Africa, go across here and around to the back side, and I'm still in, wherever it is, in Africa. It's a little bit hard to do this without being able to see what I'm doing. Okay, so one of the things that was bad about those earlier ones was these cuts, but what we see here is not really a cut. This point here is right next to that point there. We just have to go on to the other side. And so that was the concept that my colleague Richard Gott came up with. I think it's fair to credit him with that thought, is that if we do a two-sided flat map, then we can get rid of this cut problem and come up with a much better map. And so that was his contribution. He was very excited. And that's basically how we made it into the Time magazine's Best Inventions of 2021, is this notion that we can just think of this as two folded things, front and back, and improve the metrics that I was showing you dramatically. So in terms of those 6 metrics with the weighting that's standard in the cartography world, this map is better than any of the ones that were popular before. So that is what was popular, what Goldberg and Gott and I did about a year ago. But what I want to talk about today is a slight modification of this map. This is the azimuthal equidistant projection here, and the similar azimuthal equidistant projection from the South Pole. And so those projections are well known, well understood. As I already said, the latitude goes linearly with the radius here and also here. And so that was a question that came up in my mind. Is this linear representation of the latitude, is that really the best thing to do? And that's what I've spent a lot of time on last summer and in recent times. And that's what I want to talk about for the rest of today's lecture. And so let's get into some of the details of that. So here's a picture just showing that it's two-sided. And so the thought that I had was, what if I took Earth as a large rubber ball? Maybe not this big, but imagine you have a rubber ball with the Earth on it. And this rubber ball is made out of rubber. And thus, just imagine that the rubber is essentially infinitely thin, but nice and rubbery. And imagine that we could insert inside this ball a ring, a metal ring. And we could put it anywhere we like, but let's imagine we put it around the equator. And I edited this picture a little bit to show it. Okay, so there's the ring going around the equator inside this rubber ball. And now imagine that this ring has a little app associated with it, and this ring can be made bigger. It can be made into a bigger and bigger ring, and maybe I can control it with my iPhone. Say, get bigger, stretch the ball, make it stretch, 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 stretch. As we stretch it out, it will flatten, 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 flatten. And if I stretch it enough, the ball will become flat. And there, physics will kind of describe what's the ideal shape of this flattened ball. Will the latitude really go linearly with radius, or is it something else? And that was something, since I like physics as well as operations research, this was something that inspired me to look into this, and it turns out to be quite interesting, and that's really what I want to talk about for the rest of this lecture. So let's start thinking about the physics a little bit, and then we'll get into the minimization, and it'll be a little bit more back into the operations research realm of things. So here's a little diagram I made. So the ball's three-dimensional. I'm only drawing a two-dimensional picture, but think of the z-axis as pointing straight out of the screen, straight into your face. And so I'm not drawing the z-axis. I'm just drawing the xy plane, and we've sliced the rubber ball, and that's what I've drawn here is the blue here. That's the slice in the xy plane of the rubber ball, but there's still a rubber ball. I just don't show it in this picture here. And so I'm assuming the equator is on the horizontal, the x-axis. The north and south pole are up here at plus and minus 1 along the y-axis. And I'm not showing the z, but it's there. And now each point on the surface of the ball will get stretched to a different point as I move the ring. So the ring has gotten bigger, and so it's stretching out the equator, and the whole thing's shrinking a little bit. And so let's let the new coordinates be f of theta and g of theta. That's the coordinate points corresponding to the original point, which was angle theta down from the North Pole. So these aren't exactly polar coordinates where we measure up from the x-axis. This is a slight variation where we're measuring down from the vertical axis. So let's let theta represent that angle, and then this is f of theta and g of theta. Okay, and so we could look at this at any slice, but all the different slices, all the different angles at which we could slice through here will look the same there's a symmetry when I extend the ring. So I really only need to look at this two-dimensional representation of the three-dimensional ball. And this really describes everything, because all the other directions that I could orient this thing is exactly the same. So to describe the physics, I really only need to look at this two-dimensional slice through this three-dimensional ball. Okay. All right. So let's go on to the next slide. So we're going to do a little bit of math, and then we'll get into an optimization problem, and then we'll solve this optimization problem. So, so the x and y variables will denote the coordinates in the unstretched ball, and I'll use x tilde and y tilde to denote the coordinates in the stretched version of the ball. And so as a function of this theta here, x is just, well, if it was polar coordinates, it would be cosine theta, but because we're measuring it from the top down, it's sine theta. So x is sine theta, y is cosine theta. And over here, we have x tilde and y tilde, which are these functions f of theta and g of theta. And these functions f and g are the things we need to figure out what they are by understanding the stress minimization problem. So according to physics, the shape of the stretched ball will be such that the integral over the ball's surface, the whole two-dimensional surface of the ball, of the magnitude squared of the stress tensor is minimized. That's one of the things I like about physics. Real physics often involves, understanding real physics, describing real physics often involves minimization problems. And since I'm an optimization person, there's lots of interesting things in the physics world. And this is one. And so let's go into the details here. So let's let sigma of theta denote the stress in the direction tangent, I typo, of the tangent to the circle, and let rho of theta denote the stress in the direction perpendicular to the two-dimensional plane that we're looking at here. So here's the stretched ball. So there's some stress on here. The rubber's pulling on things. The rubber's saying, "Oh, you made me bigger. I've been stretched." And so there's the stretch. I don't know if you can see my cursor a little bit here, but stretched tangentially here. And then there's a stretch that's perpendicular. So I don't really draw that, but it's the fact that the ball is being stretched in the direction that's out toward our face. And we could also talk about a perpendicular stress also, but because we're assuming this ball is infinitely thin, it's made out of rubber, and there's no air pressure inside the ball that we're thinking about. We're not thinking about compressing air inside it, which would make the problem more complicated. We don't have any perpendicular stress to think about. So we only have two kinds of stress: the stress that's sort of tangent to this line here, and the stress that's sticking straight out perpendicular to our plane here at this point, f of theta and g of theta. And I want to write down those two stress functions, and then I want to minimize the integral of the sum of squares of those two things. So let's consider just a tiny little piece here on the original unstretched ball. So we have x and y, and then we have x plus dx and y plus dy. Small little distortion here, and those distortions can be represented in terms of a little d theta. And so let's do that. And so if we go back to the previous slide, x of theta is sine theta. So dx d theta is cosine theta. dy d theta is minus sine theta. Just have to differentiate these things. And so we have dx squared plus dy squared is cosine squared plus sine squared. And we take d theta squared. Then we take the square root of that, take the d theta out, and we have cosine squared plus sine squared, which is 1. The square root of 1 is 1. And so how much we've stretched this with these assumptions is just equal to d theta. So that's not stretched, but that's just sort of the angular size of this little piece over here before we stretched it. That's how big it was in an angular scale. It's just d theta. But over here in the tilde side of things, on the stretched side of things, we have to do a similar kind of calculation of dx tilde squared plus dx tilde, dy tilde squared. And let's take a look back here. Dx tilde d theta is f prime, the derivative of f. Dy tilde d theta is g prime, the derivative with respect to theta of g. And so dx tilde is f prime of theta d theta. So dx tilde squared is f prime of theta squared d theta squared. Dy tilde squared is g prime of theta squared d theta squared. Theta squared is d theta squared is multiplying both of these things inside the square root, pull it outside the square root, and we have the square root of f prime squared plus g prime squared inside this square root here. And from these, the stress is the ratio of these things, -1, because if the ratio is equal to 1, there's no stress. So sigma of theta is this distance, this width, this whatever, d theta tilde, if you like, divided by d theta, -1. So I take this and divide by this, and all that happens is the d thetas cancel, and then I subtract 1. So there's how much we've stretched things in the direction that's along the tangent here to the surface, the tangent of the slice. And then similarly, we got to do the same kind of thing for this rho. Rho is the perpendicular thing. So here, how big was the circle at a constant latitude up here, or a constant angle theta? That circle got stretched to a slightly bigger circle. What was the circumference of that latitude up here? Well, that would be, what would that be? That would be, this is sine theta is how far out we are here. And so that would be 2 pi sine theta. So the original circumference was 2 pi sine theta, but now we're out here at f of theta. And so that's now the radius, if you like, of this latitude. And the circumference of this latitude would be 2 pi f of theta. And so how much was it stretched in that direction? Well, it's 2 pi f of theta divided by 2 pi sine theta. The 2 pi's cancel. It's just f of theta divided by sine of theta. If that's equal to 1, then the stress is 0. So we have to subtract 1, just like we did up here. So that's the sigma of theta, and that's the rho of theta that will go into our integral to figure out the total stress integral, which is written here. So we're integrating from 0 to pi over 2, because that's where theta goes, from 0 to pi over 2, sigma squared theta plus rho squared theta. Now, of course, this is actually a two-dimensional, we're integrating over the entire ball. the surface of the entire ball. So this is just one integral. We also have to do an integral in a different longitude, not just latitude. And the integral in longitude at each angle theta is, as we said already, it's their circumference. So that gives us the 2 pi sine theta that we see here. So we originally had a 2-dimensional integral, which I didn't write down because the inner integral on the longitude direction was just 2 pi sine theta. And so we get this integral here in integral over theta from 0 to pi over 2. And the question is, what are the functions f and g that minimize this thing? Well, if I didn't have any constraints on here, I would just take f to be equal to sine theta and g to be equal to cosine theta, and then this would be equal to 0, and this would be equal to 0, and that would be 0, and that would be the minimum. Don't do anything if I didn't have any constraints. So this is a constrained optimization problem. I'm going to impose constraints. So here I've just written down constraints that are the definitions of sigma and rho, which we wrote in the previous slide, that relate them to the f and the g. But the main constraint here is we want to stretch this so that it's flat. I would like to figure out the stress where g, that was the vertical component in the stress thing, where g of theta is equal to 0 for all theta. This is the interesting thing, and this is why I highlighted it here. But there are a few other things that are important for the analysis we're going to do in coming slides, and that is f of 0 is equal to 0. Why? F of 0, that's up here. This point here is still at the top. We don't get a scissors out and cut this thing here. The North Pole is still the North Pole. It's getting closer to flattened, but it's still at the North Pole. So f of 0 is equal to 0. And also f prime of theta is non-negative for all theta. And that's also obvious from this picture here, that as theta increases, f increases. I'm pulling this thing out. And so that's really, if you like, we can say that's just part of the physics. And let's not worry about having to prove that that's true. That's just, this is being stretched. It's getting bigger. So f prime of theta is greater than 0. F of 0 is equal to 0. And these are the definitions of sigma and rho. Now, that g of theta is equal to 0 for all theta means that g prime of theta is equal to 0. So now I can just get rid of g here. And now it's just the square root of f prime squared, but f prime is non-negative. So the square root of f prime squared is just f prime. So sigma of theta is now just f prime minus 1. And so everything got much simpler, which we'll see in a few slides here. So the question is, relating back to our azimuthal equidistant projection, is this linear in theta? That's the fundamental question. Is f of theta equal to theta, or maybe equal to a constant times theta? That's the fundamental question that I wanted to know the answer to. And I didn't know the answer to. And now I do know the answer to. And in about 20 minutes, you'll know the answer. But right now it's a question. And at the moment, we don't know the answer, but here's a conjecture. Oh, maybe not. Maybe it's linear. We don't know. Let's try to find out. This is what inspired everything for me to do in these following slides. Okay, so we have an optimization problem. Let me go back to it. Here's an optimization problem. This is what's called an infinite dimensional optimization problem. My variable is the function f of theta. Usually in operations research, your variable is a vector x, x1 up to xn for n some dimension. And we write x without the subscript sub I to represent the vector. Here we don't have a finite dimensional vector. We have f. F is our variable. And it's a function of theta. So it's not just that it's even infinite, it's a continuum of values of theta. So f of theta, for theta from 0 to pi over 2, these are our variables in the optimization problem. So that's an infinite dimensional optimization problem. And I don't know how many of you studied this in the past. There's a whole subject of infinite dimensional optimization. It's called the calculus of variations. I'm guessing a lot of you know this. Maybe not all of you know about this. And so I'm going to go through the details. I hope it's not too boring. It's interesting to me, and I hope it's interesting to you. So here's our stress function. This is the objective function that we're trying to minimize. S as a function of this F, here it is written with the G gone. The G prime squared is gone. And so this is the function we are trying to minimize. We're trying to find the function F that minimizes this. And following the ideas of calculus, we're now going to introduce a perturbation. Let's call it, I don't know if I want to call this delta F or DF. I'll probably switch back and forth, but this is just another function. This is how we're going to perturb a given function F by some values of theta will be changed. And so this is our perturbation function. If we were in finite dimensional calculus, this would be like a delta function. I'm changing x3 out of x1 to xn. If we were just changing x3 or x pi over 6, this would be a delta function at pi over 6. But the beautiful thing about calculus of variations is we don't just focus on delta functions. We let this be any distortion, any perturbation, where we can distort all the different values of theta any way we like, any way we like. But then we're going to multiply that distortion by epsilon, and then we're going to compare the distorted version to the undistorted version as a function of epsilon, and then divide by epsilon, because that's making it get smaller and smaller, and take the limit as epsilon goes to 0. And this is like the definition of a derivative. And a critical point in the world of calculus are places where the derivative, the vector of all derivatives, is equal to 0. And so if this is equal to 0 for all delta F's, then this is a critical point. And that's what we want to find, because when you're optimizing, optimal points are at critical points. So that's what we want to do. So, okay, I'll probably go kind of fast through this because we're not going to have a whole lot of time here. But the algebra is really simple because this function F, let me go back here a little bit. Look at this. If this were finite dimensional, this integral would be a sum. And these F's would be just components of a vector. And so this would be like, and the sign of theta would just be numbers, just data, if you like. And so this would be a sum of squares of affine functions of the data. And F prime is just a difference of two. So this is also like an affine, a linear function of the data, of the variables, sorry. Not the data, the linear function. So this is the least squares problem. Everybody who studied statistics, this is just like a least squares problem. It's a sum of square deviations, if you like. But this is infinite dimensional version of a least squares problem. But as we all know, in least squares, there's only one critical point, and that critical point is a minimum. So I could just say that and just find this critical point. But we're going to go through a little bit of the detail since we have the time. And so I wrote down here in careful detail, for example, this second row here. There's a minus sign out front. Let me make believe I have this factored out minus sign here. This is F prime of theta minus 1 quantity squared. That's this thing right here. But it's being subtracted because of this minus sign here. So it's a minus and a plus and a minus rather than a plus, minus, and a plus. And the thing I wrote above it is the same thing, but with the epsilon perturbation parts. And so the epsilon perturbation parts, because the F prime got squared, you get this more complicated thing here with an epsilon term and an epsilon squared term. And the cross product thing just has one epsilon part here. So anyway, we can write all of this stuff down. And here's the nice thing, which I hope is clear from the way I wrote this. This cancels with this. This cancels with this. This cancels with this. This cancels with this. The plus 1 and the minus 1 cancel. This plus 1 and this minus 1 cancel. Most of the stuff cancels here. This doesn't cancel with anything, and this doesn't cancel with anything. So I still have those two things. These two things don't cancel, so I still have those two things, and these two things don't cancel. But everything else canceled. Oh, and by the way, I have this 1 over epsilon here, which I wrote here. And in the bottom line here, I've divided by the epsilon. So there was an epsilon here, it's gone. There was an epsilon squared here, it's now epsilon. Okay, so I brought in the epsilon in the denominator and canceled things. So this is a fairly simple expression. And now we want to take the limit as epsilon goes to 0. So we're taking, so here, I just rewrote the previous line, and now we're just taking the limit as epsilon goes to 0. And okay, that just gets rid of these two things here. And so we can rewrite this, well, it's just these 4 terms now. And let's introduce a simpler notation, since this is the analog of a derivative, directional derivative in finite dimensions. And let's call this DSDF. And so what do we have? We have DSDF is this expression that I just had on the previous slide. But let's write it in a little bit simpler way here. This is f prime of theta minus 1 times the derivative of delta f of theta plus this expression here times delta f of theta. And of course, we have this sine theta out here. And so we want a critical point. We want this integral to be equal to 0 for every choice of delta f. And this is where calculus of variations becomes a little bit more sophisticated relative to finite dimensional calculus, because we need to understand what does it mean to set this equal to 0 for every function we could think of called delta f. And that would be easy if there weren't this delta f prime. The derivative of delta f appears here. If this weren't here at all, let's just imagine for a minute that this isn't here at all. And I'm saying that the integral of something, some function of f times delta f times sine theta has to be equal to 0 for every choice of the function delta f. The only way for that integral to be 0 for all choice of the function delta f would be if the thing multiplying delta f was equal to 0. That would just say f of theta over sine theta minus 1 times sine theta has to equal 0. That would be simple. But we have this other factor here, or this other term, I mean, which has the derivative. If I can convert this derivative to a delta f, and then write this just as a more complicated expression, again, involving something times delta f, the logic I just expressed could be applied to that more complicated thing. And how can I get rid of this derivative here on delta f? Well, I can do something called integration by parts. I can integrate this and differentiate this. And that's the next slide. There's the thing. I want to integrate this. I want to differentiate this. And I don't have a whole lot of time left, so let me maybe go kind of quickly here. But anyway, I'm going to integrate this and differentiate this. This is a product of two functions. So I'm going to have the derivative of this, which is f double prime, times this, which is sine, so that's what's here, plus this, which is f prime minus 1, times the derivative of sine, which is cosine, that's that. And then I have the integral of this, which is delta f d theta. But as all of you folks who remember integration by parts, when I switch things around like that, it's got a minus sign. And there's also a boundary conditions thing, which at 0 turns out to be 0. And at the upper limit of pi over 2, I get this expression here. And so for what I had for this term here in this integral, I'm now going to change that to this more complicated expression here. So now I have 0 equals this thing minus this thing with 2 more terms added in here, which are the 2 things that I had over here. And so those things are here. And by the way, I multiplied through by the sign. And so here we go. We want this expression to be equal to 0 for all choices of this perturbation function, delta f. All choices, which means that this thing here has to be equal to 0. Because if this isn't 0 for all theta, then we can find a delta f where this integral wouldn't be 0. And similarly, this thing up here has to be equal to 0 for the same basic reason. So now we have a differential equation. So we went from that integral being equal to 0 to a differential equation. And here it is, a second order differential equation involving sines and cosines. And the boundary conditions we have are that f of 0 equals 0, as you remember. And also what we just discovered a second ago is f prime of pi over 2 has to equal 1. So second order differential equation has to have two boundary conditions. Here they are. Okay, so in some sense, we're almost done. We could do this two ways. We could refresh our memory of how we learned to solve differential equations when we were young, taking calculus courses, which is what I did, by the way, myself. I solved this this is not an easy differential equation to solve. This literally took me a few days, but I just did it by myself. And then several months went by and I decided it was time to write a paper, an interesting paper about this. And when I was writing the paper just a month or two ago, I'm like, you know what? I should check to see Mathematica if it can solve this differential equation, or maybe even Matlab. And I'm not really a Mathematica or Matlab differential equation person. In fact, I've never done that in my life until a few months ago when I was thinking about this differential equation. So maybe a lot of you have used Mathematica or Matlab to solve differential equations. I only Googled how to do it literally a couple months ago, and here's how you do it. Oh, sorry, not quite yet. Oh, yes. Before we do that, I did want to make one comment. The big question was, is f of theta equal a constant times theta a solution? Oh, I hit too many slides here. Is f of theta equals theta a solution? Well, let's try. If f of theta equals theta, then f prime is equal to 1 and f double prime is equal to 0. So this is 0, this is 1, this is theta, and so this is sine theta times cosine theta minus theta. But we want this to be sine theta times cosine theta minus sine theta. Theta and sine theta kind of are similar, at least when theta is small, but over by pi over 2, they're not that similar. And so that's kind of interesting how these are very similar, but they're not the same. And so a linear azimuthal equidistant projection is not exactly correct. So that's the first thing we just learned. And here's the Mathematica approach. For those of you who are good at Mathematica or done these things in Mathematica, look at that. I've changed f to y and x and theta to x, because in Mathematica it's standard to use x and y as a function of x rather than f as a function of theta. So I just did a notational change, but other than the notational change, this is exactly the same equation. There's the two boundary conditions, and there's where we're declaring that y of x is the function and x is the independent variable. And the output of Mathematica is this function here. Look at that. That is not very simple looking. It's got logs, it's got cotangents and tangents and cosine. It looks like complicated, actually. And by the way, the solution that I derived myself is equivalent to that. It wasn't exact. The way I derived it, I didn't write it exactly that way. I wrote the same thing with thetas, not theta over 2s, but of course you can convert between the two with trigonometric identities. But my equation is exactly equivalent to this. And look at how complicated it is. And you can do the same thing in Matlab. There's a few more lines of code in Matlab. Well, I could have shortened this a little bit actually, but anyway, here it is in Matlab. And the output produced by Matlab is even more complicated looking. It's even in the complex plane. I is the square root of -1. We have e to the I theta here, and we have I over here. When I saw this, I was like, did Matlab do it right? I literally spent hours of my life checking to see if this function here is the same as this function here. And the answer is yes. Matlab just wasn't as good at reducing it to something simple as Mathematica was. But these two things are mathematically provably the same, but I'm not going to show that to you folks. And here's the amazing thing. You plot this function, which MATLAB. I'm good at plotting things in MATLAB. That's what I use MATLAB for. Here's a plot. The black line here is the function that we just wrote down. It's this function. F of theta is this black line here. The red line is a straight line which connects this point to 0. Look at how close it is to a linear solution. It's really, really close, but it's not linear. This plot is what totally excited me, is that we have an interesting, non-trivial, infinite dimensional differential equation to solve an infinite dimensional optimization problem, and we get a solution that's almost a straight line, almost linear, but not quite. And the last thing I wanted to mention is, okay, that was a critical point. How do we know it's actually the optimal? And as I already mentioned, this is an infinite dimensional analog of a least squares problem. In least squares, we know that we're minimizing, it's convex. There's only one critical point, and that critical point is a minimum. But if we assume that we don't know that a priori, we can also compute second order differentials associated with any direction, any delta f. We can figure out the second order differential, which is this limit here, which you can write it down, and it's not hard to repeat the stuff I showed you on that complicated slide before. And you can also write this down. It turns out the epsilon squared cancels with the epsilon squared in the numerator because this is quadratic. And so there is no epsilon. We don't even have to take a limit. This expression here is this expression here, no matter what epsilon is. And the cool thing is, this is squared. This is squared. This is squared. These are all non-negative things. And between 0 and pi over 2, sine of theta is non-negative. Everything in here, 4 pi is non-negative. Everything here is non-negative. This is greater than or equal to 0, no matter what you choose for your perturbation function delta f. Therefore, we really did find a minimum. Okay, I'm almost out of time, and basically that's all my slides. I mean, I could show you the solving the differential equation if you want to see it, but maybe only if people ask to see it, we'll go with that. So I'll stop the screen share if you like, or maybe I can go back to it. And are there any questions? There's some chat questions, or there's some Q&A questions. When in doubt, integrate by parts. Thank you, Frank. And Arno Petter's projection, or Bucky Fuller's Dynaxilian. Okay, I know Arno Petter's and Bucky Fuller's. Well, good question. It would be fun to do it different ways. You'll get the same answer. Yes. It is intuitively obvious that those two functions are the same. I'm not sure which two functions we're referring to here. But anyway, anybody want to speak a question? I don't.
Sure, Bob. Quick question. Have you produced maps with both the linear and the optimal form? And can you tell the difference?
I haven't. And the reason I haven't is because I'm 99.99% sure that I wouldn't be able to tell the difference because that perturbation is really small. Yes. So the azimuthal equidistant is just fine, actually. But it's interesting to see that it's not exactly what physics would produce.
Right.
Any other questions? By the way, I did make a web page if people would like to see it. Should I show the web page I made? I could share screen again.
Sure.
Yeah, please.
Pull up my browser, which is over here. Pull this over here and open a new tab and go to my home page and make this bigger so you can see it better. And okay, so all you have to do is know how to spell my name to find my homepage. You can just type Vanderbei into Google and my webpage comes up or just remember that it's vanderbei.princeton.edu. Either way, go to my webpage, scroll down, and I have an Earth map app that I made here, which you can click on. And this is fun because it has a few different features. For example, we don't have to have the North Pole in the center. We could put New Jersey in the center by clicking on New Jersey here. And now there's New Jersey in the center. And you can also spin the map if you like, so that you can kind of get a better sense of this connection here, that it's really two sides of the same thing being shown as if they're next to each other. And for those of you who would like a higher resolution, I even have a higher resolution version of the same thing. And now if we click on New Jersey, it might be a little more obvious that it's New Jersey, or maybe not. There we are. New Jersey's in the center now. Wherever New Jersey is, right there. I also have different versions of this. Oh, I don't have as many versions here as on some of my other versions. Okay. I don't have a link to my biggest. Or do I have a bigger link here? No. So unfortunately, I'll add this link. There's another one called Big with GER added in there. And this one's really big. In fact, it even takes some time to download. But there it is. And this one has more options in the little click bar here. And this version I just made today. Not for this seminar, but for, I got an email from somebody who wanted to see this. And how long is it going to take before it pops up? There we go. There it is with latitude and longitude lines, and also country boundaries. And so now if we click on somewhere in the middle of Europe, hopefully Europe will pop up in the center. There you go. And I can go back to more full size, and you can see the country boundaries of the various countries. And anyway, so fun stuff. Okay, it's after 7 o'clock. Any other questions? Let's stop the share.
Well, I'm going to applaud. Thank you, Bob.
Thank you.
It was fun. It brought memories back of calc. I did get some private chatter that said that one person was very much afraid of calculus of variations back then, but you proved that it can be solved.
Yeah, and it's helpful. And I mean, I kind of agree with that person that when I was learning these things when I was young, it was presented in such a way that was so different from regular calculus that made it a challenge. And that's part of what I was hoping to do today, is not make it seem as different from regular calculus. But I don't know if I succeeded, but that's what I hope for.
Well, once again, thank you.
Thank you.
We're going to stop recording now.